Good afternoon, everyone. Welcome to the last webinar in the Smart series of webinars for calendar year 2022. And we are fortunate to have speakers from Stone Ridge Technology to talk on a very exciting topic, the utilization of GPU-based simulation software in the context of CO2 geological storage. It's going to be a tag team presentation. We have Dr. Vincent Natoli, who's the president and founder of Stone Ridge. He's a physicist by training with degrees from UIUC and MIT. He's worked for ExxonMobil before founding Stone Ridge. And the focus of his work has been on high performance computing, both in physics and also in engineering, more recently in subsurface flow simulation. We also have Dr. Leonardo Patacchini, who's the regional director, Europe and Middle East for Stone Ridge, based in Milan. He's also a physicist by training, also with degrees from MIT, also with about 10 years of experience in the oil industry. So we see some elements of commonality in the background between the two speakers, but right now they're all practicing reservoir engineering, particularly reservoir simulation, and we look forward to what I hope is going to be a very interesting talk. So without further ado, welcome, and over to you, Vincent.
All right. Thank you, everyone. I'm Vincent. I have Leonardo Patacchini with me. We have about 40 minutes to talk to you. I just spent 5 minutes fixing my microphone. Sorry about that. I'm going to focus on our company, our team, introducing that, and Echelon, which is our principal product. I'm going to talk about the unique features of Echelon, which differentiates it, I think, in the industry, and why we think it's an excellent platform on which to build carbon storage technology. Leonardo is going to go into more technical details on CO2 storage, and he's going to show a few case studies. So to start, Stone Ridge is a U.S. company. We're founded in the United States. We have an Italian subsidiary. Leonardo is coming to us from Milan. So we have offices in just a little bit north of Baltimore, in Houston, Milan, and a presence in Dubai. The company skills and the DNA of the company is really centered around computational physics, reservoir simulation, and high performance computing, everything you would need to make a leading edge high performance reservoir simulator. I do want to mention our key partner, which is Eni, the Italian energy giant. That's why we have an office in Milan. Eni has worked with us for the last 4 years. They have done joint development with us. And we have just, in November, started something we call the Echelon Consortium. And I have a little slide about that. This is our management team. I'm quite proud of it. We have Leonardo with us today. Ken Essler is our CTO. He's on the call and will answer some questions if they're directed to him. Karthik Mukundakrishnan is our director of R&D, comes to us from Dassault with a great background in CFD. And Klaus Wiegand, senior scientific advisor, he led development at ExxonMobil on their reservoir simulator for over 20 years before coming to us. So that's our team. Echelon is our product, and that's what we're here to introduce you to and answer questions about. So to say a few words about it, Echelon is a full-featured, high-performance reservoir simulator. It's used around the world on business-critical assets right now. Eni, in fact, is using it on, has it deployed on over 60% of their assets around the world. The unique thing about Echelon is that it was designed from inception to run on GPU, which means that the data structures, the architecture of the code, and especially the algorithms are all designed to run on tens of thousands of cores that you get on a GPU. Echelon uses what's called Eclipse syntax. So Eclipse is, I would say, the leading simulator in the industry right now. It dates back to the 1980s, but it's the most widely used syntax for input and output in this industry. So Echelon can read the Eclipse input deck files, and which allows a transition to the code in a much easier way. So what Echelon offers is ultra-fast simulation for the largest of models. Because we've designed it for GPU, and I'll go into that in a little bit more, we can also do ultra-high throughput for ensembles. So generally with ensembles, you may have smaller models, but you want to do thousands of realizations. So we can get incredible throughput on workflows like that. So some other technical facts about Echelon. It can run anything from a laptop to a supercomputer, as long as you've got an NVIDIA GPU. It can run on Linux or Windows. It can run on a single GPU or multi-GPU inside of a server, or multi-GPU across multiple nodes. So we've run it on hundreds of GPUs as just to test its capabilities. What can you do in terms of model size? Well, for a 1 million cell black oil model takes about 4 gigabytes, and a typical NVIDIA module or NVIDIA GPU today would have about 40 gigabytes. So you can fit a 10 million cell black oil model on that, or alternatively about a 4 or 5 million cell compositional model with say about six components. So you can do quite a bit on standard NVIDIA technology. I want to talk a little bit about, switch gears here and talk about the demand for simulation and the supply of simulation in our industry. And I'm going to point to 4 things here. First, there's just kind of trends in the industry. There's greater focus on existing assets. It's a little bit more difficult now just because of government friction and policy to do exploration. So there's a focus on getting the most out of the assets that we have. There's also an interest in doing ensembles for uncertainty quantification, which means doing hundreds or thousands of realizations of models. And this wasn't even possible 20 years ago when I was at Exxon and I was working on Empower, which is the reservoir simulator that Exxon developed at that time. It wasn't possible to do this because the simulators didn't have the capabilities or the speed to do it. The third thing I want to point to is, I think of interest to this group, is the new challenges that are coming to the industry from attempts to simulate CO2 sequestration, hydrogen storage, geothermal, and other, so-called green technologies. Generally, these require finer resolution grids and also additional physics, which will increase the demand for computational intensity. And then there's the digital transition or digital transformation. Companies have different definitions of this, but generally it means, using the data that you get, integrating it into broader workflows, and also incorporating machine learning or AI, which in most cases need huge volumes of data for training. Echelon can provide that, or you need a fast simulator to provide that. So that's on the demand side. All these things are pointing towards more computational intensity, more physics, more finer grained grids. You want to do more models. You want to create giant data sets. What do we see in terms of what the HPC world is offering? So on this timeline, I'm showing a number of different simulators that have emerged in the industry over the last 40 years. And when I look over the last 40 years, I see 3 epochs of high performance computing. I see the serial epoch, which is marked by computing on single core chips. I see the parallel epoch, where we're computing on multi-core chips, 2 cores, 4 cores, 16 cores. And then the epoch which we are in now, which is the massively parallel epoch, which was initiated by NVIDIA when they introduced GPUs for general purpose computing. And what I want to say about Echelon is that Echelon is the first full GPU commercial simulator. So we designed it specifically to run on these massively parallel chips. And you can see that in each epoch, there's a collection of applications and codes that have been born into it, that have been designed for it. So you take Eclipse, which is one of the most commonly used simulators. It goes way back to the 80s. It was designed for serial computers, single core computers, but of course it's been, it's been shepherded forward into the parallel era. And as well for the parallel epoch, we've had a number of codes that were designed specifically for that architecture. The reason why you do this, and I just wrote a blog article about this, is that to get the best performance, you need to design for the architecture that you're going to run on. So because we've designed Echelon to run on GPUs, we enjoy certain advantages, I would say. And here are three of them. The first is obviously performance. So GPUs on a chip-to-chip comparison with CPUs, GPUs are 10 times more powerful. The second point is capacity. So one single GPU node with four NVIDIA modules in it has the equivalent compute power of 20 CPU servers. So you can really shrink your data center. You can do things in a much higher density, more compact manner. And then in the overall economics, the operating costs for GPU turn out to be roughly 5 times less than CPU. So let's look at these one at a time. First, on performance, on the left, I have a graph of memory bandwidth plotting GPU versus CPU over the last 12 years or so. And you can see that there's a large and growing gap between the two. Why is this important? Well, most engineering codes, and I include Echelon in that, and reservoir simulation codes, are bound by memory bandwidth. That's how fast you can move data from memory into the computing elements. So the more memory bandwidth you have, the better off you are in terms of your capability, at least, for performance. So what this chart shows is that, wow, those GPUs are really delivering capable hardware. The corollary to that is, can you use it? And on the right, I make the point that yes, we can. When on the right, I'm plotting memory bandwidth on the x-axis and a normalized speed on the right. And so what I've done, I've taken 3 models, the blue triangle, the orange circle, and the green, the blue square, the orange circle, and the green triangle. And I've run them on 5 generations of NVIDIA hardware from Kepler all the way up to Ampere. And I've normalized the speed to Kepler, so that's why it's all 1. And now I've plotted their the relative speed up for each of those architectures. And what you see is this beautiful linear curve or linear fit that tells us that Echelon is efficiently extracting the performance that you can get out of the memory bandwidth that's available on the chip. Now, Hopper comes out in this month or next month, and it's expected to be delivering 3 terabytes a second. We expect that our performance will jump up again. The second point was capacity, and what I show here is a single GPU server running Echelon on the left and 20 CPU servers on the right. And the illustration here is to say that both of these configurations deliver 8 terabytes a second. So from a reservoir simulator's point of view, I've got the same amount of power there, except I've got it in a much smaller package on the left. Of course, you have to have a code that's developed to run on GPUs to extract that power. And the other point about this is just on that single server with 4 Ampere NVIDIA modules, you can run models up to 80 million cells black oil or 50 million cells compositional. It's a very, very capable. To give you some reference there, typically today companies are running models in the maybe million to 2-3 million cells. 10 million cells is a lot. Now, but part of that is because software has limited them in their ability to run larger models. So that's capacity. And finally, there's economics. And so you can just go on AWS. What does it cost to get a leading edge GPU today? Well, it's about $4 an hour to get a GPU. It's about $2 an hour to get a state-of-the-art CPU. Twice the price, 10 times the performance. So it turns out to be about five times more effective or more cost effective. And it's the same story on power consumption, twice the power, 10 times the performance. So 5 times the overall efficiency. The last thing I want to talk about is the Echelon Consortium. I mentioned that at the beginning. So we have been working with Eni, the Italian energy company, since 2018, and we have begun or initiated what we call the Echelon Consortium just last month. It's open to membership to organizations. And the consortium model is a partnership of organizations that are formed to advance simulation technology. So a company like Eni comes in with different skills, different interests than a company like ours. We come in with very strong computational physics, high performance computing. Eni comes in with, first of all, they have models to run, which we don't. We don't own assets, and they have a strong idea of where and which direction they would like to see simulation technology to develop, because there's many different directions or types of models that can be addressed. One of the directions that they're very interested in is the CO2 sequestration. So just some of the features of the consortium. One is that it provides perpetual, unlimited access to Echelon for the organization joining. It's an opportunity for organizations to lead the industry, not just license code from us, but actually lead the industry and help us vector the development of Echelon's capabilities. So you have steering rights for the development. We meet in the committee. We have equal representation on the committee. And the idea is to advance both the performance and the quality and the features of Echelon into the future. There's also a lot of benefits in just knowledge transfer between organizations. So with that, I'm going to hand this over to Leonardo.
Echelon has been developed as a simulator for the oil and gas industry, but in fact there is a rationale for using such a simulator even in the context of carbon capture and sequestration simulation. The first reason is that one of the target geological formations where to perform CCS are depleted oil and gas fields. And in this case, it's typical to inherit geological or reservoir models from the previous operator. So it is important, let's say for the sake of continuity, to be able to use the same tool and model the same processes that were modeled in the previous life of the assets before moving to the carbon sequestration phase. And in fact, even when one is interested in modeling carbon capture...
Welcome to WebEx. Enter your access code or meeting number followed by pound.
On the depleted aquifers, especially when performed by energy companies, it's also useful to have the same tool, especially in terms of training, so that everybody uses the same software. So I have a couple of slides quickly recalling what our software can model in terms of underground physics. We can model most fluid models that are used in the oil and gas industry, so black oil and compositional reservoir simulation model with equation of states. We have several rock physics models, rock fluid models with hysteresis, which is also needed for carbon capture and sequestrations. Complicated grids, many types of wells and well models, especially designed for gas production and gas injection, which are also useful in the context of CCS. And we perform enhanced oil recovery, both with gas injection and also water-based, so low salinity and polymer flooding. In terms of field management, we have complex well controls, which allow to model reservoirs with several wells and complex gas management. We have very rigorous convergence criteria, which is important, especially when we perform sensitivity analysis and ensembles modeling, because one wants to be sure that the differences between the models are really the models and not sensitivities in the numerics. We can couple multiple reservoirs together. We can couple to our own surface facility network simulator, which also could have an interest in the concept of CCS to model the surface carbon pipelines. And we can couple to external geomechanical software such as Abacus. But others would be possible as well. I have a couple of case studies that I want to show. They have all been published, so there is nothing confidential here that would illustrate the capacity of our simulator in the context of oil and gas models. The first case is a field called Mango. It's a synthetic model, but the field is real. It is an undersaturated oil reservoir. It's produced with WAG, so water alternating gas process. It has 6 components, and we have 2 variants of the model. The first variant has 5.7 million cells. The second variant has 21 million cells. And there are a couple of results I want to show you here. The first one is on the bottom right of the slide. What we show here is the runtime of the model versus the hardware on which it is run. Each vertical bar is the runtime on a specific GPU configuration, and the horizontal axis is the inverse of the memory bandwidth of that configuration. So on the right, you have 4K per 80, and on the left, you have 4 ampere 100, which is the most recent GPU available. And what you see is that the runtime is inversely proportional to the bandwidth. So this confirms what Vincent was mentioning at the beginning, which is that every time a new GPU comes out, you just take the same code and the same model, and it will run faster. And this is proven here on a real asset. The second slide and results on this model are really results of the simulation itself. And what I'm showing here are 4 plots for the 5.7 million cell case. On the top left, I have the gas-oil ratio produced for a certain number of GPU configurations. So we can run the model on 2, 4, 8, 16, or 32 GPUs. And of course, you can see on the top left that the field GR doesn't change. So the simulator is quite stable when we change the number of GPUs used for the run. The number of Newton and linear iterations of the solver doesn't change. So this proves again the stability of the simulator. However, the elapsed time is reduced as you increase the number of GPUs, which is indicating that the simulator scales as the hardware increases. And the very same observation can be done with the 21 million cell model. So really, we can run large models. The solution is practically independent on the number of GPUs, so the simulator is robust, which is very well adapted, as I said earlier, to Ensemble's modeling. There is a good performance scaling as the number of GPU increases, so you can run large model, give it more GPUs, and it will run faster. And of course, we are paying attention to the accuracy of the result. In this case, we see that the refined model needs more iterations because we take smaller time step, and this is just to make sure that we don't exceed time truncation error. So this was the first case I want to show. I have a second case related to oil and gas industry before moving to CCS applications. This is also a case that has been published in a journal, so there is nothing secret here. This is a large, giant oil field in the Caspian Sea. The grid is somewhat smaller than the previous one. It's 1.4 million cells, but it's dual porosity, dual permeability with local root refinements. We have 8 components. It's a supercritical fluid and more than 200 wells. The strategy of production is reinjection of produced gas, sales management, because there is a limited amount of gas that can be sold, so we cannot produce more gas than what can be rejected, because otherwise we would have to flare the gas, which we don't want to do. And this is translated into injectivity constraints. What I want to show here is not specifically results from the fields, because I will not be able to show you this, but again, the robustness of the code. And to show this, I have 2 plots. The first one shows the number of active producers versus time as we increase the number of GPUs, and we see that it's practically unchanged. And the right plot shows the number of Newton or nonlinear iterations versus time as we increase the number of GPUs, and again, it doesn't change. So this is a proof, again, of the numerical stability of the simulator. Now, after showing these 2 examples of application of Echelon to the oil and gas industry, I will move to the second part of this demonstration, which is what we can do for CCS applications. Now, of course, you are all familiar with the process of CO2 sequestration, so I will be quite quick on this slide, but what I want to say is that it is expected to play a major role in achieving the worldwide climate controls. And in terms of simulation, it has several requirements. There are 4 main trapping mechanisms. This is a very used and probably too much used schematic illustrating the trapping mechanism for CCS, but there are 4 main mechanisms. Structural trapping and residual trapping are 2 mechanisms that can be simulated with tools that are designed for oil and gas applications. Structural trapping involves migration of lighter CO2 towards the caprock, and this is fluid flow. And residual CO2 trapping involves trapping of CO2 by snap-off during secondary imbibition after the CO2 injection has stopped and the water rises up. And this is modeled with hysteresis, which is also available in all oil and gas reservoir simulators. There are nevertheless requirements that are specific to CCS and that are usually not available in mainstream reservoir simulators. The first of these trapping mechanisms is solubility trapping, because of course CO2 has a small but non-negligible solubility in water. And the second is mineral trapping, which is usually active at a much longer time scale, but requires geochemistry for the mineralization of CO2. There are simulation challenges. What I show on the right is just to give you an idea of the length scale that we're talking about. It's the Zmeheia area close to the troll field offshore Norway. But the reason I'm showing this specific example is because I have simulation examples of this aquifer later on in the presentation. The scale of aquifers under which we plan to perform CCS are really large compared to reservoir simulation. So we need large models. And we also need high resolution to represent heterodynamic instabilities. We basically need the resolution of the grid to be fine enough to be fine enough to resolve the physical diffusion of the process. Also, we need forecasts of hundreds or even thousands of years to assess the storage capacity and integrity of the trap. And this requires very high computational power, fine grids, large models, long duration. We also need to simulate CO2 in aquifers, but also in depleted reservoirs. So we need tools that are also able to model oil and gas fields. The physics is complex. We have to model both convection and diffusion. The geology is complex. We have to distinguish matrix and fracture flow. And there are models that we don't really know. We have hysteresis model in oil and gas reservoirs, but we are really not sure yet what the best models are in the context of CO2 injection in water. We may need thermal and geomechanical modeling as well, depends on the case, but these are additional complexities. And we do not have thousands of years of CO2 sequestration history to calibrate our models. When performing simulation of oil and gas fields, we have history, we have analogs, we have 150 years of oil and gas production history. This is not the case for CCS. What steps are we taking in our company to model CCS in echelon? We started by the first of the physical processes that are not available in mainstream oil and gas simulators, which is modeling gas-water equilibrium. This has been presented at the ECMOR conferences a couple of months ago with our partners at ENI. There are several methods to model thermodynamic equilibrium between water and gases. Some of them involve Henry's constants, some of them involve very complex EOS. We've taken the approach of taking equation of states that are usually adopted by the oil and gas industry with some modifications that allow them to treat polar components such as water. So the equation of state that we have selected is the Sorad and Whitson EOS, which is an ad hoc modification of the Peng-Robinson equation of state. And it works reasonably well for carbon injection applications. And the phase properties, including the water density and viscosity, are modeled from correlations. The first results that I want to show you today of echelon with gas-water solubility is a scaling experiment. So what we've done is we've taken a very simple sugar cube model with two components, gas as CO2 and then water. The model is initially saturated with water, so it's representing an aquifer, and we have a CO2 injector in the water producer to keep the pressure constant. We have checked the accuracy of the model versus a reference CPU simulator, and we verified that the solution is correct, both in terms of pressure of the injector and the producer, and then we perform scaling experiments. So what am I referring to as a scaling experiment? We take the sugar cube model and we tie it horizontally several times in order to increase the model size without changing the model physics. And what this allows us to do is measure the performance of the code in terms of million of cells day per second versus the size of the model itself. So what you see on the left are three curves. Each curve is for a different number of GPUs. So blue has 1 GPU, green has 4 GPUs. And we see that as the size of the model increases, the performance increases linearly and then starts to stagnate. So this shows that the efficiency of a GPU simulator is maximized when there are enough cells in the model to saturate the GPU bandwidth. So for Volta 100 GPUs, typically you need about 1 million cells to saturate the bandwidth. The second example I want to show is a real model. So this is a Zmeye field. The reservoir model for this field, or rather should I say aquifer, is publicly available. It can be found on the Equinor website. It has 1.5 million cells, 5 producers to model the depletion for the nearby troll field, 1 CO2 injectors, and about 250 years of monitoring after the CO2 injection. So what we see here is a map from the top of the gas saturation, so gas being CO2 in this case. And we compared the result from a black oil modeling. Black oil modeling meaning that the CO2 and the water are modeled with fluid tables. And the right map is where CO2 and water are modeled with equation of state. So with the Peng-Robinson, with the Somerden-Wilsonians that I mentioned earlier. And we see that after about 150 years, we have a very good agreement in terms of CO2 extent and the migration. Now, if we do the same model without accounting for gas dissolution, what we see is that the CO2 plume moves much further and reaches a secondary trap on the east. So this shows that modeling of CO2 solubility is very important in terms of volume modeling, but also in terms of security of the storage, because the speed of movement of the plume is very, very different. What I want to show here is also a comparison of solution and non-solution in terms of result itself of the simulation. So what we see here is the evolution of the average aquifer pressure versus time, with or without solubility. So there is a difference. And this is the performance. Now, I will not show you comparison with other tools, but what I am showing here is comparison of echelon versus echelon with and without modeling the CO2 solubility. And what we see is that it goes from 2000 to 2400 seconds with the equation of state. So the cost of accounting for water solubility is very small, even with the equation of state. The black oil simulation is, of course, much faster, about half the time, but the black oil approach is only applicable if you have CO2 and water. It will not work if you have more components. So what is a roadmap for developing CCS capabilities? So thermodynamics is there. I've shown you examples where we account for equilibrium between the CO2 and the water. We will release in Q1 2023 a version of Echelon that is able to model gas and water together, which is appropriate for saline aquifers and depleted gas reservoirs. And later in 2023, we will release a version of Echelon that can model three-phase, meaning that it would also be applicable to CCS modeling in depleted gas condensate or oil fields. In terms of geochemistry, we don't have geochemistry capabilities yet, and the objective is to model CO2 mineralization reactions. So our plan is to perform preparatory work over 2023. And the most important aspect to consider is that we have to decide whether we want to model the reactions within the simulator, implicitly or not. That's a secondary topic, but do we want them in the simulator, or do we want to perform some iterative coupling with third-party codes, such as FreeQC? Each approach has advantages and drawbacks that we could discuss, and then give us a couple of years for the implementation from 24 to 25. The third capabilities that we have to implement is thermal modeling. Why thermal modeling? The reality is that we may need to account for Joule-Thomson cooling around the injectors, and also the impact of temperature on rock integrity. So it can lead to fracturation at the injectors, but we also want to investigate aspects such as cap rock integrity. And the work is going to start in 2023, again, preparatory work to decide the formulation, and then implementation in 24 and 25. So this is the slide for Vincent. Vincent, I will let you conclude.
We've talked about our product Echelon, our company. Echelon is a full-featured, industrially robust simulator. It's deployed worldwide on ANY assets and other of our customers. We have industry-leading performance with this unique technology that's been designed specifically for massively parallel GPUs. The company itself has 10 years experience in GPU-based simulation, and we've led the field. We've done many, many firsts in the industry. We've published along the way. We've done some so-called hero calculations over the years. In 2016, we simulated a billion cell model to show that we could. And then a few years ago, we simulated 100,000 models in an ensemble with ANY and published those results. We are focused on the simulator engine itself and our unique technology. There's a lot of great pre and post tools out there, and we're not adding to those technologies. We're completely focused on making the fastest, most stable, and most robust simulator engine that we can. As far as alignment with the Smart Group and the DOE, Echelon offers transformational capabilities in simulation through speed, through advanced physics, and through model size, as Leonardo's case studies have pointed out. And touching on the ML and the AI focus in this group, we have the ability to generate training data that can be used to train AIs and machine learning workflows better than any other competitor.